This is Cody Jackson for Cody, and this is going to be probably the last Python video that I'm going to do in terms of introduction to Python. That's why I've put the Capstone title on here. I do want to emphasize, especially for this video, that I am not going to cover all of the code for this project. I'm just going to highlight certain parts of it to demonstrate how you would put a full Python program together. If you want all of the dirty details for this program, basically start to finish, it is in the Learn Programming in Python book. And so that will actually walk you through how to complete this project if you want to recreate this on your own. That being said, let's jump over to our code. So I guess I'll point out, this is how I created this particular project, and now that I think about it, this project is about, well, since it's the new year, this is probably about 3 years old now. And the way that I make programs doesn't necessarily stay the same, but this is as close as I would say is a ideal way of laying stuff out. So you have different directories, packages, things like that for different purposes. The EC environment, that's created by Python when you are creating a virtual environment. So you don't need to worry about what's included in there. Models, I have in here the package fuel farm, package for HMI, functionality, which is just a Python file, components, another Python file, and we'll cover these in a little bit more detail in a second. HMI is actually some Kivy information. Kivy is a graphical framework for Python that allows you to make cross-platform and cross-device programs that have a graphical framework. Kivy was not the most ideal solution in terms of making a graphical framework for this program. Let me just run it so that you can see what it's actually supposed to look like. So this is a field service and transfer system. So this is actually based off of a airport model of how they receive fuel from tanker trucks and how that is put into the airport trucks for transport to the planes. So we actually talked to the fueling people at a airport and came up with this diagram based off of that. So you have your 1,000,000-gallon fuel tanks. There's 2 of them, a variety of valves, 3 pumps for the fuel, so for redundancy, or if you need to take one down for maintenance and things like that. These little valves. So the valve obviously is just 2 triangles pointed together. This valve here, or I should say these valves here, are back pressure regulating valves. What that means is they regulate the pressure on the outflow of the pump, and to make sure that you always have a constant pressure coming from the pump regardless of what the pressure and volume flow coming into the pump is. It's always a constant value coming out, because obviously you don't want it fluctuating when you're filling up a tanker truck full of fuel. You may have too much coming out, you may have not enough, things like that. These are pressure regulating valves. which basically just says if the pressure gets too high on the output and the regulator can't control it for whatever reason, maybe downstream a valve was shut off without shutting off a pump, it will cause, it basically opens up like an emergency release and puts the fuel back at the beginning of the pump. So it basically just recirculates until you can get the downstream part fixed. You have your trunk connections, sampling lines to test the fuel before it goes into the trunk. There's actually a manifold for fueling the larger airplanes that you would just have to have like half a dozen trucks to fill. You can fill them directly. So I know that this is probably going to go over the heads of a lot of people. But on the other hand, I kind of hope that it gets you thinking that when you're making your programs, it's not just business applications that you're going to be working on, like a text editor or a website or something like that. When you program, you can literally program anything that you can represent. And so in this case, we used Python to recreate this environment of a fueling station for an airport. But it could be any industrial application, anything, anywhere. And obviously, in terms of the fidelity for this environment, I had to reach back into my nuclear training from the Navy in terms of system engineering and stuff like that to recreate pressure drops and flow rates and things like that. I don't expect everybody to know that, but also recognize that as a programmer, the more well-versed you are in non-computer science related applications or systems, the more chances you are of being able to get a job. You could get a job at an industrial plant. You could get a job at a warehouse, programming their automated forklifts, their system, the logistics systems, things like that. So I guess what I'm saying is think outside the box as a programmer, because nearly every thing that you can do now in terms of a job is going to be programmed to some extent. And so if you learn the basics of some engineering fields, whether it's mechanical engineering, civil engineering, electrical engineering, you can get a job in these areas programming those types of systems. So I'll show you what this program actually does. So we have a whole bunch of valves here. We've got the 3 pumps that are highlighted in red, just to make them stand out. If we wanted to take fuel from tank number 1 and put it to truck connection number 1, we would open valve G1, valve G5, and turn on pump number 1. Actually, I want to show you something really quick. So without anything going on, I've programmed this to populate this table to show what pressures, flow rates, things like that are in the system. So our tanks have a level of 36 feet. And through some mathematics, you get a static hydraulic pressure. So that's the pressure due to the weight of the water of 13 psi, pounds per square inch. And a flow rate, if the valve was not, if the valve was open, of a lot, nearly 20,000 gallons per minute. And that's because you have 36 feet of water putting on that. Now, you may not think 13 psi is very much, but atmospheric pressure is 14 psi, and so this is coming out of a 6-inch pipe, I think it was, in my calculations. Like I said, it's been about 3-4 years since I created this, and so I don't remember all of the details. But anyways, you have a high flow rate, relatively low pressure. If you know anything about hydraulics, you know Bernoulli's equation: high pressure equals low flow, low pressure, high flow. And so that's why we have a relatively low pressure with a high flow rate. All of our valves in the system are closed. Our pumps are turned off. So there's no flow, there's no pressure coming in other than what's on the entrance to our valves that are at the tanks. So if we open those valves, turn on the pump, and repopulate the list, you'll now see our valves are position 100. So 0 is closed, 100 is fully open, and obviously you can have any amount in between there because you can do that with regular valves. The pressure is coming in, and this is the pressure that all of these valves are seeing. So valve 1, 2, 3, and 5, you can see 1, 3, 2 is still seeing the pressure from tank number 2, 5. So even though valve 3 is closed, it still sees that same amount of pressure coming from the tank. And that's why 3 is in there as well. We have a flow rate coming from the tank. That is what's being seen by the valve. We have the pressure coming out with gate valves. There's no significant pressure drop, and so that stays the same. Flow rate stays the same. Our pump, we have pump number 1 turned on. It's spinning at nearly 1500 RPM. It's using almost 1 watt of power. It has 13 psi coming in. Because it's a pump, it's going to increase the pressure, so the pressure goes up to 50, but it can control the flow rate. So instead of nearly 20,000 gallons per minute, we have 355 gallons per minute, which is significantly different. Again, high pressure, low flow. And so that pressure is being controlled by the pressure regulating valve here, and then that would go to the truck. So I don't expect you to necessarily understand everything that I'm talking about. Just recognize that this is all done with Python code and some knowledge in knowledge of engineering principles and things like that. So anyways, that is the HMI package. The fuel farm package has our functionality and components. Again, we'll talk about those. The piping systems package, this is where all of the heavy lifting of the back end code is being done. And so we have our pump package, storage tank, and valve. Each one of those has its own Python file that contains the physics mathematical models for each of those things. We have a directory for unit tests. We have the piping, we have models, and it just depends on how you want to create those tests. V-environment is another virtual environment directory that's created by using a virtual environment. I'm using pip environment, and so I have 2 pip files here for that. Some utility formulas, and then some code that I was doing for testing manually some of these code banks without actually going through full-blown unit tests. So we'll start with the easy stuff. Utility formulas. So if you've taken physics in school, a lot of this stuff should sound similar to what you hopefully remember. So we have constants for gravity, specific weight of water, density of water, all that stuff. And we've got the values that were for imperial. We are not using metric in this case. Calculate the flow rate due to gravity. And this is based off the pipe diameter, the slope, the coefficient of the pipe, which is the roughness. That's all calculated here. This is not higher mathematics. This isn't calculus or anything like that. This is just basic algebra. The static pressure, which is the height due to, or the pressure due to the height of the liquid. The pressure from the flowing water, things like that. So these are all just utility formulas that are used by other files within the program. We'll take a look at the valves real quick. There's a lot of header information that I put in here. This is based off of PEP 8. And so PEP 8 is the Python documentation that provides guidelines, recommendations for a common use of how to document your code, how to make your code look, how many lines there are between each code block and stuff like that. And so one of the things that it recommends is in your doc string for your file, you talk about what classes are there, if there's subclasses, things like that. And then I personally just put my author, the date that I created this, so yeah, about 3 years ago, and internally what version I'm doing this. I update this version number every time I would change a file. Importing the math library from Python, and this is kind of cool for PyCharm. It will give you the docstring information from anything that has a docstring in it, really. And then you have the ability to go in and actually get the legitimate documentation from python.org. So, create a class of a valve. This is just a generic valve. Could be a valve in your home, anything that controls your water. This is just a generic valve. So, I don't expect anybody to know this unless they've gone through some sort of engineering curriculum or if they have an interest in this. But a lot of the things that I have within the program are engineering terms for things. So you have your system flow out, your pressure drop across the valve, pressure in, flow in, the position, all of that stuff. And then we start calculating different things for these valves. In this case, there's a coefficient of the valve based on the valve diameter, and how constrictive that is for fluid flow through the valve. And so we calculate that, which basically means that if someone wanted to use this program for something besides fuel flow, they could do that. If they wanted to use this in a water treatment plant, they could theoretically use this program with minor changes, and then just change the values that are being put into these formulas. So in this case, we just have a generic diameter for the pipes, which I think I said was about 6 inches or so, which is a pretty good sized pipe. But you can go in and you can change that diameter. So if you wanted to use household pipes that were like 1 inch, maybe 2 inches, you could do that. If you wanted super massive industrial things that are 8 inches or bigger, you can do that. We calculate the pressure drop across the valve. So the pressure in minus the pressure out tells you what the pressure drop is across the valve. And that's based off of the flow coefficient of the valve design, blah, 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 blah. A bunch of stuff that you're probably not going to be aware of, but just accept what I'm telling you. The pressure drop is based off the flow rate through the valve, the specific gravity of the fluid that's going through it, as part of PEP 8, it does recommend having what exceptions you have defined for this particular method. In this case, I have a zero division error. What type of return are you giving? Float is our return type. And then what is being returned? The pressure drop across the valve. And so we have a calculation here, and that, because it is using classes, we just have an instance of the pressure drop that we're updating. So we're not technically returning anything. We are just updating an instance. Flow out, not going to talk about. Pressure, blah, blah, blah. So here's a property that we have. This property is is the position of the valve. So if you remember, with properties, we have the actual property, so what value is returned to you. And then we have the property setter, which changes that value that would be returned. And so this is basically your getters and your setters from other languages. But for users, they don't need to know what the black box internals are of this. They just need to know if they call position without any arguments, then they get what that valve position is. If they call position and give it an argument, then they can change that valve position, either open, closed, halfway open, things like that. And we have some methods that define a fully open, fully closed valve, and changing the instances of various parameters, flow out, pressure, position, things like that. Now, that's all of a generic valve. So if you remember when I was talking about classes, I talked about how you can have a generic parent class that has everything that any specific instances of that class might need. And then you have subclasses that actually define those specific instances of that parent class. So we have a generic valve, and then we have gate valves, globe valves, relief valves, all these other types of valves that if you've ever done any sort of plumbing or anything like that, you should understand. So a gate valve does not cause any sort of restriction on the flow going through. It's basically either fully open or fully closed. So we can read the position, which basically says the gate valve is open, and that's what it tells the user. The gate valve is closed. Sorry, the gate valve is closed. Gate valve is open. And if it's partially open, it will tell the user as well, because gate valves should not be partially open because that damages the valve. We have a method of turning the handle. You give it the position. It uses the position of the valve to call the close or the open methods, again, because it should be open for fully open or fully closed. We define globe valves, which is just your standard valve, say on your outside water faucet for your garden hose and stuff like that. Relief valves have some special criteria. Now this is interesting. Our other valves are just purely inheriting from the generic valve class. Our relief valve, because it has some special characteristics that are not part of normal valves, we actually inherit the base properties of the generic valve, and then we add some specific parameters for relief valves. So super is a call that says that we are going to inherit everything from the parent class, and we are going to, in the relief valve class, we are going to add some special criteria, which is open pressure and closed pressure. But everything that is in our super initialization is inherited from the valve, the generic valve class itself. And so for those two values, the open pressure and the closed pressure, we define those separately. Everything else that we use is inherited. And so the open pressure and the closed pressure are just characteristics of relief valves. When does what pressure causes the relief valve to open, and when does it reset when the pressure drops? I'm not going to go through everything. Just recognize that there's a lot of physics calculations in here, and so I actually went ahead and got the mathematical formulas for all of these parameters and created algebraic calculations for all of this fluid flow, hydraulics, plumbing themes. So we have our tanks, we have our pump, and this is the pump flow rate, the pump pressure, the power that's used, all that type of stuff. So that's all of our piping systems. So if we go back to our fuel farm model, then we have our components, and this is where we take all of that calculation files that we just looked at under piping systems, and this is when we actually create actual objects that are going to be used in our diagram. So we have tank 1, we have tank 2, given them names, set the level, like I said, 36 feet, the fluid density, specific gravity of the fluid that's being used, the outlet diameter, 16 inches, not 6 inches, so I was incorrect. That's why you have such a high flow rate, because you have about 1.5 foot wide pipe, so you have effectively no pressure, regular atmospheric pressure, and you have a huge pipe that's unrestricted, and so you can have, tens of thousands of gallons flowing through each minute. It's basically a tiny river. We have a slope for the outlet pipe, and so it's going to be, in this case, 0.025 degrees, and that basically, it's almost flat. There's enough of a slope to actually get the water flowing without any assistance. You don't need a pump on the tank to get that water coming out. And like I put up here in our, this should actually be in a dock string, but we're just defining stuff. So anyways, we're assuming a 36 foot tall tank with a 1 million capacity, and this gives us how many gallons there are per vertical foot of water, of the fluid that's in there. 16-inch pipe. Now, we did have density and specific gravity that we saw previously in our utility program. These are different. So density and specific gravity for water is just 1. For jet fuel, it's going to be slightly different, and these are the numbers that I got from documentation. So obviously you can change those values depending on what fluid you're working with. Are you using industrial chemicals? Are you using aviation fuel? Are you using vehicle fuel? Whatever you need, as long as it's a liquid fluid, you can use a lot of the code in this program to play with. So based off of the parameters that we've given our tank instance, we can calculate the static tank pressure, the flow due to gravity, things like that. And then we do the same thing for all of our valves, the fuel pumps, the other valves that we have. So everything that we saw in that initial schematic where we were opening the valves to get the numbers, those are all part of these components that we have defined in this file. The functionality file takes those components that we've just defined and then creates different specifications depending on what is going on. So if our valve number 1 is open, then we call the gate valve open method, and you can see where we've imported these. So the components, the file that we just looked at, is being imported as FFC, so fuel farm components. So we call the open method, we determine what the flow rate and the pressure values are going to be based off of the tank pressure, which is going to be based off of the height of the fluid in there. Close the gate valve, open, close, all that stuff. Gate 3, and I'll show this on the schematic so you can figure out what I'm actually talking about. So gate 3 is this valve right here. So what's interesting with number 3 and number 4 is you can have flow coming from tank 1 or tank 2. That's why this schematic is drawn the way it is. You can take fuel from tank number 2, pass it through number 2, or gate valve 2, gate valve 3, or sorry, 4, 3, 5, and 1. So you can basically take fuel from either container and use it to fill. So if tank 1 was empty and they're refilling it and you need to fuel a plane, you can take it from tank 2. Valve number 6 can obviously take fuel from either one, and if you really wanted to, you could open up all the valves and put all the fuel going through valve number 6, and that's accounted for in the calculations that I made in here, is what is going to be the input values based off the flow rate, based off the pressure coming from both tanks. So anyways, that's all put in here. The way you have to write Python language, this is not easy to decipher just by looking at all the stuff, and so that's why I have so many comments in here to explain what's going on. Yes, if you're using proper variable naming, you can understand what's going on. So gate valve number 6 pressure in equals gate valve number 3 pressure out. But, you know, I did put in some extra comments. Pressure from tank 1 greater than tank 2. Oh, that's something else. So in this particular model that we have here, because we do have 2 tanks, and if you wanted to open the outlet valves for both of those tanks, then whichever tank has the higher amount of liquid in it, that's going to have a higher pressure. And so that one is going to be feeding more due to the higher pressure, more flow coming out, because the other one can't compete. You know, it's obvious. And so for gate number 3 and its complementary gate number 4, you have to account for which tank has a higher pressure due to higher height of the fuel that's in it. Same stuff. Gate 5, gate 6. So gate 5 and 6 are using our utility formulas, the pressure to the head, to calculate the pressure that is being sent to the pumps. And there's a reason that you need to account for that. The basic thing is, for certain types of pumps, you have to have a certain amount of pressure coming in, or the pump just doesn't work correctly. As the fuel is used, you can change the level of the tank to show obviously that the fuel is being used. The height of the contents in the tank go down, and therefore the static pressure that is coming in, or I should say coming out of the tank, is being decreased as well. And I like to have a else statement just in case myself or somebody who's using this isn't paying attention and uses the incorrect parameters. So if you have tank 1, if you have tank 2, if you give it a different value, tank 3 or something like that, it's going to tell you that it's incorrect. What would probably be better in this case is to change this to, instead of just having an else here, to a try and except. So you would try tank 1, tank 2, and if it's neither of those, then you get in a value error exception, and then you print invalid tank number. We also have our formulas for how to work with the pumps, and for these particular pumps, all of their parameters are based off the speed, the RPM of that pump. And so that's going to dictate what the pressure and the flow coming out is. And so that's basically it for the functional part of the application. I'm not going to talk about Kivy because, quite frankly, working with Kivy with this particular application was very, very frustrating. I was using version 1.10. They're now up to version 2, so it hopefully would be easier nowadays. But all of the tutorials and the documentation that I used 3 years ago really talked about how to use Kivy to make games for tablets and phones and stuff like that. For actual desktop type applications such as this, at least version 1.10, I would not recommend using. I would recommend using something like Qt or maybe even a web page or something like that. So this was very painful to work with. And that's actually one of the reasons why this looks the way that it does. So this schematic is actually just a JPEG that we had created. And the Kivy part of it is to create these buttons here. And you'll see I don't have the ability to scale this particular picture. And that's on purpose. If you scaled it, the JPEG would move around, but these buttons are hard coded in to these particular positions because trying to get them to move at the same rate as the schematic picture itself was almost impossible for me. And so I found it easier just to force the user to deal with this static image than to do anything else. So we're going to move away from the Python code and we're going to talk about the tests. So our tests can be run, and we have a whole bunch of tests here. So our initial conditions is basically what is our starting condition for all of these tests. So what is the valve position? What flow rate do we have? What pressure do we have? All that type of stuff. So this is all of the initial conditions. And then each test after that uses that information to basically run the test. And so I'm using pytest. It's not currently installed on this computer, which we can do. So because we're testing centrifugal pumps with this file, we have to import the centrifugal pump from our pump file. And then we go ahead and we test all sorts of things. So is the pump speed running at 450 RPM if we give it a pump speed of 450? If the pump is stopped, does it actually say the pump is stopped? Now, this is not the most ideal for how you would use an actual real-world application. I mean, this was used in real-world applications for work. But in terms of telling people what's going on, this was just printing to a console rather than a more useful GUI dialog box and stuff like that. But the concept is still the same. Based off of the parameters that you give the test, is the output that you get what you programmed into it. So this could be a number, it could be a string as it is in this case. It can be anything that you want to compare to what's actually being generated. If we run our tests, pytest goes ahead, it runs the program. PyCharm will tell you you have 13 tests that have passed. If you want to see what they are, if they're failures, it will allow you to take a look at all of them down here. If you want to look at the tests themselves, then you'll see the standard pytest values that are being given to you. So in this case, each test is being created on a line. So get speed expected, get speed 0, get flow rate, get pressure. And then it also shows you how much of a completion of the overall tests are being done. So obviously if it hangs or something like that, you can see did it complete or not. Tells you the total number of tests that were ran, whether they all passed or failed, how long it took, and stuff like that. I think I can run a test and show you what fails. Okay, that all ran. I used this on another computer and it failed, so it is what it is. It actually does depend on the environment that you have. If you're using a different computer and it's not set up the exact same, your tests may fail for no reason. So in this case, we ran all of the tests that I've ever created, so almost 150 tests that I've created. It tests all of the valves, it tests all of the pumps, it tests all the tanks, everything. And so that was all basically just this. Make a class for what it is that you want to do, create a specific test for each type. I tend to go with what is a 0 value, what is a normal value, what sort of results do you get if you use anything that's outside of that range, negative numbers, higher than expected numbers, strings when you should be getting numbers, stuff like that. And so those, you can see all of the tests are over here for basically everything. The pumps, if you want to change the valve position, checking the actual functions that we created over here in functionality, all that type of stuff. That's all being handled by those tests. And for the model itself, we can test that. So we run all the, okay, here's the file that was failing. So the piping components work fine. The model that I have has some errors. 18 passed, 5 failed. And now here you can see this over here is all of the failures. And then you can look individually to see what passed, what failed. So our fuel components, here's everything that's being ran, which ones passed, and then you can start to see which ones fail and where. So if we actually go straight into the component, or I should say the test that failed, it tells us that it failed on line 167. So we click that, takes us to line 167, and we're looking at test gate 3, gate 4. So it's actually head of this test is where it failed. So it's telling us that the value that we received, 0, is not what was expected, 39085. And so you can click to see the difference. Actual 0, expected this number. Obviously, this would be more useful if you had a more comprehensive test and you had multiple values that were supposed to be coming in. And then it gives you a little bit more detailed information of this particular class and what the value is that you're getting. This entire method, test gate 3, gate 4, goes through and it tests all of the valves that are related. In this case, it's failing on when gate 3 is open. What is the flow rate going into valve number 6? So just for clarity, we'll go back to our picture, and you can see we have gate 3 going into gate 6. Now it's expecting all the flow rate coming from tank 1 through gate 1, valve 3 coming to gate 6, and it's saying that instead of receiving 39,000 gallons, it received a value of 0. And so what that basically means is we need to take a look at what's being calculated in our tests. And obviously I went ahead and pre-calculated what these values should be. And I will say, if you're off by a little bit, it will break. It would actually make more sense to make this less accurate, because then you get a little bit of rounding error ability. So if you actually set this for 13 instead of however many digits this is, then it would make it a little bit easier to make your tests pass while not being inaccurate. And I say this from a problem that I had where I was getting, like, say 13.1 instead of like 0.9, it was like 0.7 or something like that. So while still correct, it wasn't as correct as, the number of digits would say it is. So anyways, you have to go through, find out what the error is, and then go and determine why your actual results are not what you expected them to be. So that's really about all that I have to say about this. Again, if you want all of the gory details, it's in my book. Not that I'm plugging my book, but obviously it does go into more detail than I'm putting into this video. In case you're curious, here is what a Kivy file looks like. It's not pure Python. It's, I don't know, maybe closer to XML and JSON, because you have to define what your buttons are. In this case, we have buttons, the size. You have to deal with the layering. So canvas before is, what are you going to do before we draw items onto the picture, and then you would have canvas after and things like that. It's not the easiest thing to work with. In my opinion, PyQt is much easier, makes much more sense, and it has so many capabilities now. It's cross-platform, it's cross operating system. You can do 3D graphics with it. I think it has a module for making games. If you want to take a look at Kivy, hopefully version 2 is much easier to use. It's not intuitive. The documentation at that time, 3 years ago, was really rough. The tutorials were not good unless you wanted to make video games. And you have to deal with the box layouts and hand coding all of that Qt is very nice because it has Qt Designer, so you can drag and drop how you want the layout to be and then just code from there rather than trying to hand code everything and line them up correctly and things like that. In terms of the future of the Codamom channel, I don't see a lot of content coming in now. This was originally started by Karina, if you remember her video from way back when. She created this channel and I was just assisting her, and that turned into me creating all the content for this channel. I don't have a lot of time to do that now, with work and my own personal projects that I'm working on. And it was really designed for Karina to showcase her skills and abilities and her knowledge so she could get a job. Well, she got a job, and now she doesn't have any time to contribute to the channel, and I'm at that point myself. So this may be the last video for this channel. If you do want to see more content, especially more specific content, let us know in the comments, and as time permits, new videos can be created, but don't expect regular or semi-regular videos to appear. It is what it is, and life goes on. This is not a full-time gig like it is for other people on YouTube, where their income is based off of viewership and sponsors and ads and stuff like that. So this was really more a project of love and education and giving back to the open source world, but that's going to have to come to an end now. Again, if you want to see anything specific or even just more content, let us know in the comments, and we'll do the best that we can. So until the next video, have fun, keep learning, keep programming, and enjoy life. Bye. Thanks for watching.